Indoor agriculture faces a strict spatial constraint. To maximize crop yield, operations must optimize every available cubic inch of a limited volumetric footprint. Traditional planar rack farming approaches this problem with a linear scaling model. To increase plant count, cultivators must physically expand the width or height of their rigid shelving hardware. In closed-loop environments, the critical metric determining system viability is watts per plant, the precise measure of resources consumed to bring a single organism to harvest. Improving this metric without expanding the physical footprint requires a nonlinear geometric redesign of the grow space itself. Static, flat plane architectures inevitably reach a strict ceiling of spatial inefficiency in compact or residential environments. Breaking past that limit requires a radical shift in form factor. The Centrifugal Hydroponic BioPod solves this by utilizing a dynamic volumetric geometry to automate year-round indoor cultivation. Its core mechanism is a large-scale, low-RPM rotating barrel designed to continuously cycle a dense payload of 96 individual plants. Building large, dynamic hardware typically requires cost-prohibitive industrial machining. Relying on distributed desktop-scale 3D printers to fabricate a system of this size naturally invites engineering skepticism. The BioPod succeeds by applying a precise hybrid structural philosophy, marrying accessible 3D printed polymers with standard structural metals to achieve industrial rigidity. To understand how this functions, we have to decompose the system into its geometric, structural, and mechatronic layers, tracing the exact load paths and material science decisions. The BioPod is a complex mechatronic assembly that solves compounding physical constraints through rigorous mechanical design. The first biological constraint in a high-density 96-count payload is delivering intense, even light. This cross-section highlights the central axis. Plant notes rotate in a continuous loop around stationary LED grow lights mounted through the hollow core. Keeping this axis stationary eliminates the need to route dynamic, twisting electrical wiring to rotating components. This brings us to the second biological constraint, delivering precise nutrient water to constantly moving targets. The traditional approach relies on complex, rotating plumbing joints that inevitably wear out and leak under constant hydraulic pressure. This animated diagram illustrates the stationary misting solution. Nutrient spray nozzles in the fixed bottom drip tray automatically mist each modular plant plate as it rotates past the exact bottom dead center of the cycle. This centrifugal geometry entirely decouples the heavy, continuous biological inputs from the dynamic mass, drastically simplifying the plumbing and electrical architecture. Moving a dense mass of 96 water-heavy plants in a continuous motion introduces a severe primary mechanical constraint. Large-scale FDM 3D printed structures are highly susceptible to rotational flexing and dimensional warping when subjected to constant, shifting dynamic loads. Even minor rotational flex causes the gear mesh between the massive rings and the drive motor to bind and slip, eventually stripping the teeth entirely. The definitive countermeasure to this polymer flexing is the hybrid structural philosophy. The core of this philosophy is the integration of standard 1-inch structural aluminum square tubing directly into the primary stress-bearing components. This wireframe shows the aluminum exoskeleton. Rigid 1-inch bars slide completely through the 3 massive printed rings, locking them in perfect alignment. The frame actively transfers torque and twisting forces away from the soft printed polymers, absorbing mechanical stress. The modular plant holding plates are then secured using hot-tapped M5 threaded inserts set directly into the plastic rings.
Bolting down 16 of these plates per ring with high-strength M5 hardware creates a continuous shear web. This maximizes the structural connection points and physically stiffens the entire barrel assembly. By deliberately marrying accessible aluminum extrusions with complex printed geometries, the design successfully bypasses the inherent mechanical and structural liabilities of desktop printing. Ensuring safety and longevity also requires highly specific material science decisions for the bespoke 3D printed subassemblies. Standard prototyping plastics are vulnerable to polymer creep, a condition where materials permanently deform when exposed to continuous load and fluctuating temperatures. To prevent this, ASA, or acrylonitrile styrene acrylate, is utilized as the mandatory engineering-grade polymer for the rotating rings and the primary frame. ASA possesses superior UV stability, resisting degradation from powerful lights. Its high heat resistance ensures the frame won't warp.
Conversely, PETG, or polyethylene terephthalate glycol, is required for all water contact components, including the internal plumbing and the base reservoir. PETG provides an exceptional moisture barrier, preventing any chemical degradation, and its natural material composition makes it inherently food safe. Tailoring polymer selection to specific mechanical roles ensures long-term dynamic reliability, matching the performance of industrial injection molding at a fraction of the prototype cost. Driving the entire structure requires a precise mechatronic mechanism capable of maintaining the continuous low RPM cycle. Positioned between the base and the barrel, the drive section houses a variable speed motor mounted securely directly to the rigid 1-inch aluminum bar. This animated vector diagram details the gear reduction strategy. The motor spins precision-printed drive gears that mesh directly with gear teeth integrated into the outer circumference of the large barrel rings. The system's intelligence relies on a single-board microcontroller architecture, such as a Jetson Nano or Arduino, housed entirely within the sturdy lower base. This microcontroller constantly processing incoming environmental sensor data while executing the precise timing logic required for the light phases and the bottom misting cycles. This interface image shows the external user terminal, explicitly designed with a functional, high-density aesthetic inspired by LCARS displays to organize complex readouts. The terminal translates raw mechatronic sensor data, like temperature gradients and cycle countdowns, into an intuitive, easily manageable control surface for the user. Isolating the control electronics within the sturdy base and externalizing the interface ensures the automation system remains safe from water overspray and easily serviceable without dismantling the primary machinery. When fully assembled, the Centrifugal Hydroponic BioPod operates as a single, tightly integrated mechanical unit. The geometric design achieves maximum watts per plant efficiency by rotating the entire plant biomass around centralized lighting and targeted stationary misting. It achieves large-scale dynamic reliability through the hybrid exoskeleton, combining standardized structural aluminum with task-specific ASA and PETG polymers. This specific engineering matrix successfully bypasses the need for costly traditional machining techniques when building complex automated hardware. The design proves that accessible desktop manufacturing is entirely viable for high-load, continuous-use mechatronics, provided that structural load paths and specific material limits are rigorously respected. The BioPod is a robust, open architectural blueprint capable of enabling automated, localized food resilience inside the modern home.